It is my honor to introduce Dr. Jason Corso. Jason Corso joined Stevens on January 1st, 2021, as the director of the Stevens Institute of Artificial Intelligence, otherwise known as SIAI. He is also a tenured professor of computer science and the Viola Ward Brenning and Albert Calhoun Brenning Endowed Chair. A veteran in the field of computer vision, Jason has dedicated over 20 years to academic research on video understanding, robotics, and data science, and has commercialized university based research to benefit healthcare, chemical engineering, autonomous driving, and other applications. He has also made expertise backed policy contributions in law enforcement, laid the groundwork for improving the social environmental well being of urban communities, and co founded Voxel 51, a thriving computer vision startup which makes developer tools to enable machine learning engineers to perform rapid experimentation with their image and video datasets for improved AI methods. Jason's main research focus is high level computer vision and its relationship to human language, robotics, and data science. As the director of the Stevens Institute of Artificial Intelligence, he will oversee the long term strategy and day to day operations of the Institute as it takes on the challenges of the next 5 year plan. With an emphasis on thought leadership, engagement, and entrepreneurship, he envisions an institute that emphasizes the social relevance and impact of AI in both local and international communities. Jason came to Stevens from the University of Michigan, where he was a professor of electrical engineering and computer science. He earned his PhD in computer science at the Johns Hopkins University in 2005. Now, please welcome Dr. Jason Corso.
Thank you so much for the kind introduction, Robert. And it's my pleasure to present this webinar to the ASE community today. My webinar is entitled The Evolving AI-Human Relationship, and I will touch on its impact to education. My career has spent, as Robert mentioned, has been spent on developing high-level computer vision methods with core connections to language, robotics, and the human. The human has been at the center of my work for the last 2 decades. And as I've observed the community evolve broadly, the relationship between the human and AI systems has also evolved. And I'm happy to talk to you about my views on that today. So I'll give you some background on the AI-human relationship, then go into detail on 2 methods that explore what I see as the next generation of the relationship between AI and humans, and then touch on some comments and how this relates to education. And so, as you know, AI has really been impacted broadly by the massive amounts of data that are available. Data of humans doing things like sporting, data of biochemical reactions, data of protein reactions, data of political engagements, Wikipedia, tons of data across myriad different domains has given rise to functionalities that were only thought of as futuristic or sci-fi as recently as 2 decades ago. For example, here's a really fun video from implementation of a paper called Neural Talk, which takes a frame of a video on the fly and describes it with a natural language sentence. Okay, the sentence is sometimes wrong, but it works. It's believable. This is an implementation of a paper by Andre Karpathy and Fei-Fei Li from about 7 years ago and available on Vimeo. Just one example of the type of experiences we're seeing now. I'm sure you're all familiar with this very fun movie from the 80s that is all about coming back to the future. But I tricked you because it's not actually the movie that you saw. It was a deep fake, right? That was actually Iron Man at the top playing the role of Doc, right? AI is everywhere, across voting problems, across space travel, domestic travel, banking, finance, education, gaming, entertainment, sporting. It's almost amazing and unbelievable the impact that we see AI having today and in the future. In education, I can see numerous myriad ways that AI is actually having a near-term and direct impact in terms of tooling for education, moving what I think of as sort of well past spell check, right? We are seeing amazing tools like Perusal, which I used in my computer vision course last fall, which lets us have our students asynchronously explore not only written content and ask each other questions, ask the professor or the GSI or the TA questions, also explore video at the same time and comment on different parts of the video, what they're finding, what they don't understand, and mapping those two domains back together. Right? So this type of interactive software-based or asynchronous learning is changing the way we do education, both in terms of educators and learners, including lifelong learners. In the tool that I mentioned in Perusal, AI is used across numerous angles. First of all, it is used for grading, automated grading, right? This is an amazing help for TAs, GSIs, right? I had 180 students in this class last fall, right? Each week they were assigned reading about 10 to 15 pages of technical material. And that it was an asynchronous flipped course, also remote because of the pandemic, right? So we didn't have the resources and the staffing to go and check everyone's work. And we wanted to encourage participation beyond, more than actual being judged or criticized based on their comments. The tool directly supported that, for example. Also automated testing tools, right? Now when we see students taking like the GREs or the SATs, or maybe in the future they won't be taking those types of standardized tests, but other types of testing tools that are able to have a model of the learner or the test taker on the fly and adapt the material based on the context, based on the needs, and so on. We're also seeing rich game-based learning tools, like learn a language on your phone, and it will also adapt to your comfort level, to your experience level. Really rich tools to support education. On the other side of the education domain is the study of education practices, right? Researchers that ask questions like, what is the role that teachers play in the achievement and social skills of students in their class, right? In collaboration with the University of Michigan ICPSR, I've begun to explore questions like this, looking at actual classroom observation data, an example of which you see at the bottom here, right? The predominant research method in this domain is direct classroom observation. That means observers will either sit in the back of the classroom and observe what's happening, or they will put a panoramic camera like you see here, and observe the students and the teacher interacting throughout the day, try and do things like count the number of interruptions the teacher has. That's, there's been some claims that the frequency of interruptions in the classroom leads to worse learning by the students, right? So other questions like that are enabled by this type of observational material. Unfortunately, it's exceptionally onerous to do the coding. It's called like translation of the video into a structured representation that can be analyzed with computational social science models and so on. But if we can use AI-based video coding, it would enable repeatable, rapid, robust mapping and measurement, overcoming the significant burden of manual classroom coding, right? And this would enable the rich, repeatable study of teaching practices, learning practices, classroom management effectiveness, things like grouping behaviors, activity behaviors of the classrooms, interaction, and the impact of different forms of interaction the instructor may have with the class, right? But as you can see, even from this simple video here, I just applied an off-the-shelf computer vision method. It's not working that well, right? So maybe we even need some further methods in core AI capabilities, in this case, video understanding, to support this automated video-based coding. And perhaps to do that, we need to bring a human in the loop. And this will be some of the agenda of the talk today, right? Again, AI is everywhere, touching on myriad domains, myriad applications. If we think about it, what does AI, in quotes, because it's really hard to kind of define what collectively what AI is, but what does an AI system look like today, right? So using some humorous cartoons, let's think of it on the development side. Right at the top, you see people, let's call this the annotation phase, right? They're gathering data and they're dropping the labels on those data samples so that they can then go and put them into some other later stage factory system. This is a very huge network right now, or huge collective set of problems in data management, data annotation, ontology specification, lots of involvement with domain experts and with humans. After we have that type of data annotation, data modeling, and so on, The data moves to the training phase, right? The modeling and the training phase, where it's sent usually to the cloud, or if privacy is a concern, maybe on-prem. And we see more humans playing with the parameters, the knobs, they're tuning the models and so on. They're comparing the training set output against the testing set output. And hopefully they're finding success. The next part of the AI is a wall, right? Nothing gets through the wall except the output model, which is a small little nugget, couple gigabytes in data that then gets deployed. And once it's deployed, everyone's happy and it works like the sunshine. That's kind of like what AI looks like. Note here on the right side of the slide, the deployment side, there's no humans, right? There's no interaction with the deployed system typically. Generally, the humans are involved in labeling, in specifying the model, and then in the operations for the deployment, but that can usually be automated with things like Kubernetes or what have you. Now, there's a whole swath of startup companies in the AI ops space that are handling that deployment in a mostly automated way. But there's a lack of humans in the deployment. Furthermore, there's no interaction between the deployed system and the developed system. And this may work for certain types of problems, right? It may work for filtering pornographic material on Flickr. May work for that. It may work for some forms of autonomous driving, like lane following, or it may work for other AI for the masses type problems, where the individual characteristics of the problem or the context or the user don't matter that much, or at least we're not emphasizing that. That's old AI. What we need now, what we need to grow as a community, and what we have begun to, is moving toward personalized AI, where the individual matters in the context of the collective, of the mass, right? We don't want to throw away all of that data we've already captured. It's useful data. It's very valuable data. All those videos I showed you in the second slide, that's from a data set that my group made called Actor Action Data Set, right? We had different types of actors like dogs, cats, mice, humans, birds, doing different actions, jumping, running, flying, moving. That's a rich data set, thousands of videos that are useful for bootstrapping a model. But if I want to go and use that to understand classroom behavior, I need to adapt it, transfer the model from that for the masses problem to this personalized problem. So let's look at how that might seem or appear in two different types of problems. The first one is a deep fake-like problem, a video object removal problem here. In the top left, you see a video example, input raw video. In the bottom right, you see the main actor or participant in the video automatically removed from the content. The top right and the bottom left are the automatic segmentation output of that person, of that main content that's used to generate the removed video, the faked video, right? This is a problem in computer vision called video object segmentation. And the typical approach already starts to break down that wall between the development and the deployment side. And it does so as follows, right? So there are three main phases to researcher methods for this problem. The first is training on a base network, right? This is what we generally call in machine learning pre-training, in domain pre-training, right? So these methods are typically trained on ImageNet, which is a large image-based data set, and it just helps us train the millions of parameters of our model, of the AI model, to understand what typical images look like. And then the second phase, also on the development side of the wall, is what's called a parent network training phase. This is trained on the exact problem we care about, with the outlining of the actors or the main participants, main objects in the video. And the cost function, the way we sort of constrain the parameters of those models are on problem, right? So we know which object we care about, and we're going to penalize the method if it incorporates a segmentation for the main object outside of the ground truth that was provided by the human. Then comes the wall, right? That's the development phase. But we've taken some bricks out of the wall now, because in the testing phase, in the deployment phase, we're also going to do more training. We're going to incorporate a human at that time. And this is where a human gets to say, for the first frame of the video, what object they care about. in this case, which breakdancer or which person in the video they care about. And that's the key here. You know, most of the work in this video object segmentation problem has been built on just labeling the first frame of the video, just having a human label the first frame of the video. And there are many, many methods on this, dating back at least to half a decade, you know, in this video object segmentation problem. However, my colleague Brent Griffin and I asked the question, is there a better candidate for the human input than the first frame? You know, what if the object they want to remove from the video is not even in the first frame, which actually is a real problem we had on a DARPA project where it wasn't there. The human we cared about was not in the first frame, this person walking across the video, or at least maybe it was only the front of their foot. And so we realized we need to look at a different frame. And so this is a new type of question. We're changing the rules of the AI problem, right? Can we learn a method that will decide on a better frame to ask of the human based on the likely object they want to remove from that video? Right. So let me tell you a little bit more about that problem. And in fact, what you're seeing here are some results that show if we ask the human for every frame of the video at the bottom of this, so this graph at the bottom of the slide here is very interesting, right? So the horizontal axis is the index of the frame that is used to query the human for the segmentation that would be used then at deployment time to train or adapt the model, right? So if we ask for the 0th frame, we get a segmentation performance of 0.5. Don't worry about the exact method. Higher is better in this vertical axis. If we ask instead for the 25th frame, we're going to get a performance of 1.2, right? More than twice as much as the first frame, and so on and so forth, right? So we found in this early work we did that the actual frame that's selected impacts the video object segmentation performance significantly. You can really see what this is. So in this particular example here, this is a motorbike. The goal is to segment the human on the motorbike, right? So we get this yellow performance if we use the first frame, which is the status quo for the problem in the community. If we look at the 12th frame, we get a 69% performance improvement on the 12th frame. If we look at the 20th frame, by contrast, we get a negative 53% relative performance improvement, right? Performance drops significantly, and 20th frame is roughly in the middle of this one. If we look at the last frame, we get a performance improvement by 14%. How could we possibly know which frame to ask for, right? So it's a new problem for video, incorporating humans on the fly in this domain, right? So we want to select the best frame to do this, right? So typical methods are based on an algorithm called one-shot video object segmentation, which is just used to essentially seed the video object segmentation problem here. One thing you might guess is, well, how can we set up the problem to ask for a better frame, right? We can say, okay, I have my data set, and I'm going to, for every video in the data set, I'm going to have a training sample that says, if I select this sample, it will lead to this performance improvement or degradation. Unfortunately, it's only, this data set in question here is only about 4,000 frames total for training. That's just simply not enough to train the types of models we see in this problem or in this domain. So we had to think carefully, how can we train networks to select better annotation frames for humans? And we came up with a method that we call bubble nets, right? So assume n frames per video. Instead of predicting the direct performance of an individual frame, which would only give us about 4,000 samples, which again is not sufficient for the variability in this particular data set or in general. We're going to predict the relative performance between 2 frames of the video, giving us n square labels per video, right? Furthermore, we're going to choose k, I think in our work k is 3, k random frames for reference, and also input those to the network. Now I have n to the 2 plus k possible samples. I don't know the exact number that is, but it's significantly more than 4,219. Right? So we're going to instead train a network that predicts the relative performance between different input frames in the video according to these k reference frames. Right? Now at runtime, our model, the bubble nets model, will learn to iteratively compare frames and then do bubble sorting against the video, and finally use the highest ranked frame to send to the user. right? In this particular case, the green is the best video. And once we do the sorting, we'll ultimately put that at the right side and choose that one to query the human. And this leads to significant performance improvements across the Davis data set, right? So if we select the first frame, that's the top video. If we select the best frame according to our method, noting on the graph on the right, it's not perfect, right? We didn't select the best frame, but we selected a good frame. We get significant improvements. We don't get the humans at all in this case. We get the barrel, the wheels, and significantly fine improvement. Similar for this case here, allowing the humans time and effort to be guided at runtime, at inference time, for the problem that they care about most really helps you get better performance. In this case here, the significant drop off from, around from 50 to 70 is when the hand leaves the frame. The human in this case wanted to segment the arm, not the dog, which you might have thought would be the case. Right, and so there's some numerical results. We can just show that according to the standard way of evaluating this method, BubbleNets performs best according to various arbitrary things like selecting the first one or selecting the middle one or a random frame, and really improves the performance, right? And this is generalizable to other types of performance-based video processes as well, which we've done in later work, right? But the key here is that if we break down that wall, separating the development and the deployment phase and incorporate better human input at inference, we can yield a better system. And that system might allow us to remove a human-focused, whatever the human really wants to remove from this video. Here's an example video. Depending on the reason why this video is captured or the goal of the human, one may want to remove the woman from the video, or one may want to remove the truck from the video, depending on the task. Only when you incorporate a human on the fly can you build systems like this. That's part of the benefit of personalized AI. Right? How can we get further toward a different instance of personalization in an algorithm where perhaps we don't even know what the cost function is we want to minimize yet? Right? So let's take an example. Usually if this is an interactive talk and I give a slide like this, I can ask a question and you're going to answer on the fly, but I'll just pretend someone's thinking about the answer to what is the dog breed in this frame. Give you a second. I think this is a golden doodle, right? So maybe you knew that, maybe you didn't know that. Golden doodles are pretty common dogs in the US. What's the breed of this dog? Probably much less of you know the answer to that. It's a Bergamasco Shepherd dog. I think they're common in Britain. I could be wrong about that, but they're definitely not a well-known breed of dog. So if I was to ask you for the label, which is typically what we do in classical AI, supervised AI, you might fail. You might not be able to do it unless you're a dog expert. But if I were to ask you a simpler question, are these two dogs the same breed? Clearly, you can tell me it's unlikely that they're the same breed, right? I can vary my question, right? Are these two dogs the same breed, for example? Maybe, maybe not. They are in fact the same breed. The one on the left is my family dog. It is a golden doodle, right? But I could have even varied the question, or you could have varied your answer based on your problem, right? Maybe you care about the color of the dog, or you care about the dogness. Maybe there's dog and cat images, or you care about your dog versus other dogs because you want to organize your photo album, right? Only when you are able to incorporate humans in the loop, like you see in, for example, in iPhoto or other photo organization type applications, this is an example of breaking down that wall. Can you get toward personalization in AI problems, right? So consider a classification problem, a new problem called constrained clustering, in which we have samples in a data set, and instead of just assuming or using first principles to define our distance function, we are going to use that bootstrap model or some distance function like a simple Euclidean distance, but we're also going to incorporate constraints such as must link constraints. These two images must be linked, or cannot link constraints. These two images cannot be linked. They must be in separate clusters, right? That's a problem called constrained clustering. You can imagine the various needs or cases in which this is valuable. Active constrained clustering is an instance or situation where you actively seek during the learning process with a human or multiple humans available answers to such questions, right? This is a subset or an instance of a problem called active learning, where the classical active learning is the problem of choosing the next sample. So you're given a data set X here marked into a closed world of 3 labels, green, red, and blue, right? With big N samples, X1 through X big N. Your goal is to learn a class conditional density function, P given class label omega, P of class label omega given a sample X. In fact, that's not a class conditional density. That's a typo. We should switch those. X given omega. Anyway, that's not critical. So, given our current understanding at iteration t, p theta t, where the parameters of our model are theta or theta t, we can select we seek the next sample xt to maximize the information gain on that probability function, right? P omega given X or X given omega, right? So how do we do this? Let's look over the samples. For each sample, we can compute the current class conditional density. In this case, that looks a lot like a green sample. Would it be wise to ask about that one? You already know the answer, probably not. We're not going to gain much information either loosely or very technically from entropy or uncertainty modeling on that density. This one, similarly, it's a red sample. It's amidst the red space, the red cluster, if you will. But this one, it's in the middle of green, red, and blue. It has a uniform distribution in this cartoon example. So we should ask about that one. And if we do, we might get the answer. It's a blue one. When it's a blue one, we know what to do. In this case, we've had to go through order big N samples to figure out which one to ask about next, right? So that's active learning, a true instance of human in the loop, personalized AI, right? But when you get to pairwise constraints, the problem gets a little bit more challenging. And these pairwise constraints may be used for things like semi-supervised clustering or constrained clustering, as I said, or metric learning, or other problems in which the decision boundary or the classification problem is not exactly well-defined yet. It may be well-defined later. We may take the pairwise constraints and map them to a closed world problem, or we may map them to other problems. In active clustering, we see this cycle evolving, right? So we start with an initial distribution over the model, either first principles distance function like Euclidean distance, as we said before, or maybe we have a deep net that we're using to do distance function. And we wanted to use that actor action data set I mentioned earlier as our bootstrapping data set. Perfect example of the use of that type of off-the-shelf data for a new problem. Given the distance function, we then go and apply it to a clustering algorithm, either a simple method like k-means or something non-parametric or something like eigenvalue-based clustering, right? Spectral clustering. Then after we do clustering, we need to go and sample and query the user again, like we saw earlier, right? We want to learn from the user input to then go and adapt our distance function or our clustering algorithm to refine the method and meet what the user says should be clustered or should not be clustered, right? Interestingly, this is a harder problem than active learning, than just choosing the next sample. Why is that? Just computationally speaking, there are a quadratic number of possible constraints we can ask about, right? So for one sample, I'm not just asking about that sample, I'm asking about the sample and another sample, or another sample, or another sample. Now, certainly we have, in a case of a fully connected graph, it's the worst case scenario, but in typical graphs that we may have over data where the graphs might be inputted to us, we can have fewer, maybe average node connectivity the degree of the nodes might be something like 5 or 6, who knows, it really depends on the problem, right? But it's still order n square, which is really big. Furthermore, random constraints are useless, right? So if we just take random constraints, they'll often lead to redundant information, or even worse, as Ian Davidson from UC Davis found, the wrong constraints can lead to suboptimal results that worsen your interim clusterings, right? These are not incorrect, noisy constraints from the user. These are just the wrong ones to ask about, right? One that is in a part of the decision space or the sample space, excuse me, that will, given any answer, make it worsen your overall understanding of the the sample space, right? So we need a mechanism for constraint clustering or uncertainty measures that will make this a soluble problem. So my group has invested a significant amount of time in this problem over the last decade, and I can't really tell you about everything we've done given the time we have, but let's just look at one trick we did. Basically, we converted the constraint selection problem into a node selection problem, a sample selection problem. So we changed the O(n) square problem into an order n problem, making the assumption that when we choose that single sample, we're just going to ask about all of its neighbors. So i.e. making the assumption that it's not a fully connected graph, or that the cardinality of the nodes is pretty low. Okay, so again, given a data set X that has samples X1 through X big N, the goal is to learn a clustering model that looks a lot like the class conditional density we said earlier. Just now we have C indexing into our clusters, and we have K of them. In this case, we know the number of K clusters. We have done some work in which you don't know the number of K clusters, and there are mechanisms for also querying the user for the best number of clusters and so on. And we also have, at iteration T, some pairwise constraints, green in this case for must link, and red in this case for cannot link, that have given rise to our class conditional density over our models. Now, in this case, we're assuming a clustering model that has a probabilistic nature. There are many of them that do exist, but there are other ways of mapping these types of constrained clusterings to, say, or constraints on the labels to say, spectral clustering and so on. And the goal here is that we seek the next constraint to maximize the information gain on this probabilistic model. How on earth do we do that? Well, again, like I said, we tricked ourselves. We tricked the system. We seek the next sample whose constraints best reduce the clustering uncertainty, right? So if we're looking here, this one looks like it's part of the magenta cluster. Now, magenta does not have a name. It's not golden doodle or bird. It's just the magenta cluster. We don't need a label for it. All we are working on are class densities, or cluster densities. Here, this is a slightly better one than the magenta one because it's on the boundary of the magenta and the orange one. Here, it looks like it's an even better one because it's on the boundary of all three of the cluster ones, right? So we would ask about that one, and then we would query all of its neighbors. And that lets us yield a method that can adapt on the fly to human goals or the specific user goals, right? For example, here we have a data set where we're doing dog breed clustering, hence the motivation earlier. And our goal is to define or minimize or compute the clustering distribution by asking as few questions as possible of the human and to achieve the right classification. Only based on clustering, not based on learning a deep net classifier on top of this, just based on the clustering model, right? So in this case, it's really mapping from classification to an unknown decision space, and we're just doing clustering on it. And you could see in the graph at the bottom that evolves as we ask more questions. Our method is based on blue, and this is just using the exact thing I just described to you, and then forcing a k-means clustering method to actually group or not group neighbors, versus say random answers are the green curve at the bottom. This will repeat. Or sorry, random constraints. You can see that random constraints are not helping at all. They're redundant to what's already known in the bootstrapped decision boundary. Right, and this is a new form of personalization. I mean, I think of how this could map to, I don't know, so education is one thing, but take it to an intelligence analyst whose job is to review heaps and heaps and heaps of images and video, or even documents. Similarly, you can think about document distances over different word phrases or what have you. Every different analyst, depending on their mission, will have different questions or answers to similar questions. And this type of functionality will lead to a personalized AI that will take us sort of maybe out of the lab a little bit more into practice. You know, I think this has significant impact or potential for personalized education, right? So the notion of incorporating the human throughout the AI equation for personalization, right? And I think if the first group of bullets here, I think we're kind of at the stage of a perfect storm for personalization in AI. And I think this is based on some recent developments we've seen over the last decade or so. First of all, there are significant amounts of data. A lot of that data is for closed world classification problems or object detection type problems, or things like that, even language translation problems. So that a lot of the data is useful for classical machine learning and AI, but a significantly more amount of that data is open domain, not labeled, raw data, still useful for these types of problems, certainly ripe for constraint seeking or other types of human in the loop question answering that could give rise to new types of models. The second point where I think, second part of this perfect storm is that I think we're moving out of the lab or the closed world, let's write a paper about this new model on this data set from 5 years ago, into a world of an uncertain decision landscape, right? I don't necessarily know what the right cost function is or output space is when I'm observing a classroom. In the teacher behavior in that classroom, I have different variables or vectors of measurements like grouping behaviors and activity behaviors of students, actual content, ultimate outcomes. I have all of this information in this sample space or decision landscape. How do I map that to an AI problem? Or how do I leverage all of that so I can map it to multiple AI problems? And I think the third component of this perfect storm for personalization in AI is that there's a notion of direct individual interest and benefit from the personalization of these methods, right? Again, autonomous driving, mobility, everyone's going to benefit from having vehicles that can drive themselves, or even just do lane following to reduce accidents. But the space of problems that are for the masses is smaller than the space of problems that are for the individual, because again, of the uncertain decision landscape. So there's buy-in from humans to work with a system so that it can learn about their needs, about their problem, and so on for this, right? So I think instances of personalization that we will be seeing in the future of education are things like integrate what we learn from classroom observations, those video coding work, and other models of learners. So integrate what we learn from the masses to adapt to individuals on the fly, right? Or dynamically create content based on the context or based on the individual learner, based on the goals that they may be specifying, right? Or the creation of different novel reward mechanisms or incentivization structures that are suited to the individual that might even be mappable from one learning domain to another learning domain, like learning a musical instrument to learning mathematics. Perhaps there's commonality for learner style that could be used and exploited by these personalized AI education models. But these advances are not without concerns, right? So whenever we think about personalized data and all the data that's out there, we have to be aware of privacy, right? So it's not going away. That's an important problem to be concerned about. Similarly, I mentioned when I applied an off-the-shelf video object detector to the classroom observation earlier in the talk, it really didn't work that well, right? Why didn't it work that well? Well, the video was skewed because of the panoramic lens. The quality was not very high. I guess the frame rate was lower than typical, and so there's a lot of noise in the video. The students were all sitting at their desks, and I guess in the training data set, which was a data set called COCO, for that method, there are not many people sitting at desks, right? These AI for the masses models are not really adaptable. They're not generally going to work as well as humans can do the types of perceptual capabilities that you see. So I think there's a methodological gap between what we know how to do for personalized domain transfer and personalized AI and so on than where we want to be. But I think it's a ripe challenge problem for us, and I look forward to working on it in the future, and I look forward to reading your papers as well from it. So in summary, this talk was all about the transition that I'm observing, moving from sort of general AI for the masses to personalization in AI. And I think we're going to make significant strides across many fields, including education and things like healthcare, information management, and so on. I'm happy to take your questions. Thanks for your attention. Feel free to reach out if you'd like to have a chat. I'm available. Otherwise, I look forward to answering your questions. Thank you.
Thank you, Jason, very much for this very informative talk. We do have a couple of questions for you. I'm going to say the person's first name because I don't want to destroy any last names while I'm answering these questions. So the first one comes from Lorenz. He asks, what AI is available currently to aid human creativity, specifically idea creation, and what does the future hold?
Yeah, it's a great question. So I think there's a class of methods that are becoming popular now that are called generative methods. They've been generative models have been around for decades, but only with the influx of data and large compute are we seeing these generative models able to create data samples that are convincing, like the deep fake type examples you saw, even the removal or the addition of. And so I think these types of generative models coupled with things like random walks over the decision space of the generative model may be a good tool for creativity or idea generation. I think that's the first thing that comes to mind, but I think it's a really cool space to think about how you can have kind of like an AI peer that's personalized for you and your style or type of education of creativity, and kind of working together, almost like your tool is a extension of your individual creativity. Only when you think about personalization in AI models could you possibly get there.
Great, thank you. So the next question comes from Luciano. He says, thank you very much for the opportunity to attend this webinar. It's been really informative and enlightening to learn a bit more about the role of AI in education. The one question I have is, how close are we to have an LMS that implements the vision you mentioned of personalized learning and assessment, particularly in colleges and universities where his interest lies? As a follow-up question, if we are already there, could you provide some examples of LMS already available?
That's also an interesting question. So I think there are nuggets of instances of tools that integrate into LMSs. So one that I'm familiar with is a company called Alex, ALEKS. I believe that they are now a division of McGraw-Hill that basically has a graph, builds a graph, and I may be misrepresenting their technology, but I'll do my best, has a graph over the problem domain or the learning domain, say algebra or trigonometry or what have you. And then as a student is presented with modules through that graph, they will take a walk between nodes of the graph based on the student performance. I don't believe that is integrated into a college level or post-secondary LMS. Unfortunately, in fact, I think we have a ways to go before you'll see the type of personalization even in that tool, like I mentioned, like this Alex tool, getting into LMSs. But I think we're right on the fringe or the frontier of seeing that. Like the other tool example I gave, Perusal, it doesn't adapt to individual humans, individual learners, as far as I know, but it brings lots of these features of LMS, of AI, like grading and even selecting which questions you want to ask or present in class based on the collection from the class. It's integrated into LMSs already into at least the one into Canvas that I've used in the past. So I think we have some ingredients, some nuggets that are getting there, but it will be some time before we know the right representational models for each individual learner, and then map that to LMSs in post-secondary education.
Great. The next question comes from Toon. Thank you for the presentation. What are some positive and negative applications of the segmentation process?
Oh, interesting. So very concretely for video segmentation, it is used in healthcare, for example, to quantify the rate of tumor growth in say an MRI scan or even a CT scan of a patient. The leading or the most important indicator of progression of cancer, for example, is the volume of the tumor over time. That is work I've done prior to video segmentation, but it's the same idea, same methods and so on. It's also used across the board in entertainment. for rotoscoping. It's done mostly by humans in the past, but now we're seeing human augmentation by automated methods. It is used in, think about, instructional video, right? So I personally have benefited greatly from YouTube and task-based instructional video in terms of like cooking certain recipes or even removing a fence post from my backyard. Like great value in open domain videos where I can use text to query YouTube and find the video relevance. But sometimes videos are too long, right? And sometimes I really want to hone in a 60-minute video. And this is also for education material as well. Like I give my lectures in an LMS or on YouTube, and someone wants to remember, what did Dr. Corso say about that k-means clustering algorithm last week, right? So I want to be able to use segmentation, in this case temporal segmentation, not spatiotemporal segmentation, but similar idea, to go and do that. What are negative applications of segmentation? Well, I mean, I think the example I gave you is a negative, in my view, a negative application in some sense, right? Like removing content from video, if we can do it in a convincing manner, might have impacts in law enforcement and safety, and even in the permissibility of evidence and video evidence in court cases, for example. That's the most immediate negative thing that comes to mind. But I'm sure there are some other negative aspects as well. Like, for example, even on the flip side, if we miscount tumor growth, then it will have maybe a negative impact on the prognosis for the patient, which may lead to overzealous treatment, for example, right? So we want to make sure that our methods are performant to the users. And again, this is also why I'm an AI technologist at heart, but I'm also a firm believer that the human will remain in the loop for the foreseeable future. And I think that's critical for a level of trust and safety in these types of methods we're developing.
Next question comes from Hadi, and they said, "This is great. Thank you for a great talk. I was wondering, when you were thinking of, quote, personalized AI, did you consider the social responsibility of this innovation? And can we actually teach students how to integrate that in their work or design projects while being aware of the social responsibility of the impact of their work?"
Hadi, thank you for the question. I think you're getting at the real heart of AI. I mean, there's another talk that I've given recently about my view of the space of AI a little bit more holistically, and the role that trust plays in AI, and even like bias, and the role that data and the way we use data and different models do play in AI. I see that really as the foundation of artificial intelligence going forward. Building on top of that, we have like the critical knowledge gaps, like the ones I'm mentioning in this talk, among some others. And then on top of that, I think we have like personalized education, personalized healthcare. So at the real core, we have the role that responsibility, data, and like human plays in this situation. And I think your question about how do we teach students about this, I wish I had the answer. What I can tell you is that I believe we teach AI like it's 1985. I've taught AI courses, I've taught machine learning, I've taught pattern recognition, computer vision. We teach it like it's a set of algorithms. And of course, to learn AI, you need to understand the methods, the mathematics underneath it, and so on. But that's only one of maybe 5 sides of the thing that is AI, right? On the other side are the types of impacts you're talking about, even on the design side, right? What is the role the human user plays in the model specification or in the application specification? Really hard, rich questions. Or what about the role that data bias and data nuances play in data choice, even like this, or like the specification of the ontology for your problem, right? One problem that I've come across a lot in my professional work is the difference between, say, what to label in an image or video and what not to label now, and then next week when I change my problem, or next year when I change my problem. right? And I don't want to go back and have to touch everything. So problem choice, data choice, labeling choice. This is the getting towards a bigger picture in teaching AI and educating the next generation of AI practitioners. And at the Institute at Stevens, we are rethinking from the ground up what an AI education means and how to present that very interdisciplinary across the school: business, design, engineering, systems, and what have you. And I think when we launch our new education programs, you'll have a more firm answer to your question. But right now, this is the best I can do.
Thank you. So the next one we have is from Benil. So our approaches that you described apply also to hierarchical clustering of labels that are interlinked. Say bolts as a label and then interlinked to the various versions of bolts.
Yeah, I think very firmly one can map constrained clustering and active constrained clustering to different types of constraints and data sources. One, for example, that we had I think I cited it in the talk. We had a TKDE paper, maybe 2018, that used ranking constraints, for example, right? Like, is A more similar to B than to C, right? Or not, or is A more similar to C than to B? That induces a hierarchy over your data. And so, just given the time constraints, I really couldn't talk in too much detail here, but I'm happy to follow up afterwards if you'd like to talk through those ideas. Yeah.
And the next one comes from one of our attendees. Thank you for this webinar. I'm interested in how AI might impact project-based learning. What opportunities and cautions might be relevant in this space?
That's a good question. So project-based learning, well, certainly AI is a ripe landscape for projects in project-based learning. But let's see, if we think a little bit more out of the box, right? So when I was at the University of Michigan, I was a mentor for a program called MDP, Multidisciplinary Design Projects. And this was a 2-semester long project that put a faculty member and a company with 5 students. And their goal was to kind of solve the company gave a little bit of money, not a huge amount of money, and a problem. Our problem was, I think, segmenting or classifying different parts of an old newspapers into like a caption, a text, title, things like that. Really hard problem. It seems like it should be an easy problem, but no computer vision problem that you think is easy is actually easy. So the students working through a project has common steps, right? So I was there to help them walk through the project. But even myself, like I at the time, didn't know what lean project design was or agile methods were or other types of things, right? So I could envision being able to have an AI project mentor, AI-based project mentor, where now the learner is the team, not the individual. So a little different than what this talk was concretely about. But I could envision a learner that has a sort of a framework for what a project process should be, and then has worked with individual teams on different projects and has modeled typical behavior, typical points of failure, typical gaps, so that at weekly meetings or regular meeting, what have you, that it can present to the team questions maybe that should be answered by the team or should be considered by the team in discussion. Right, so I think that's an instance where for any task that you have, like cooking a meal or learning to drive a car, right? If there's, we can develop AI methods that can observe people doing the task now and the variations in that, and then induce a model over the task, and then watch new people executing the same task, and then be able to guide them either through visual prompts or audible prompts or other email prompts for that matter, depending on the type of task. And I think we're really ready for that type of work. And it's something that my group is already indeed working on to some degree. So I think it's a good problem space. Yeah.
Okay, and I think we have time for one more question. This is from Jose. It says, congratulations, very interesting presentation. What software do you use in your investigations? R, Phyton, etc.?
Wonderful. So I use a lot of different types of software in my research work, not including R. However, I've never used R. I guess Python right now is the language of the realm for AI and machine learning, and it's mostly because there are a few factors, right? One is that writing Python is semi easy, right? Like, okay, formatting by indentation, not my favorite thing, but in general, you don't have to define the variable types. It's a non-typed language for things like that. But it also has functional components, so I can map a function over a list of variables, which otherwise would, in C or Pascal or some in Java, like you have to write the for loop out, right? So there are really nice software engineering type elements to Python. But more importantly, it's fast to write some pretty sophisticated things, and there's a huge amount of community support around Python. And then when it matters, like when you're actually doing number crunching in your computation, it's generally not in Python, but you don't know that. It's in a library that was compiled under the hood, either running on a GPU or running in machine code through C or something like that. And I think my group has done this for ages, but we base the choice of a language like Python on the Pareto principle, right? Like the 80-20 rule, right? So like 80% of my computations happening only in 20% of my code. So let me use GPU based or CUDA for that directly, or some library that uses CUDA under the hood. But the other 20% of my processing is going to occupy 80% of my code. So let me choose the easiest thing possible to write with in that. So that's why Python is a really common language for that. Other things we've begun using lately. So for example, my company has an open source tool called 51. If you go to 51.ai, it's like an interactive tool that also has a Python library that lets you do model interpretation while you're doing data set visualization and analysis. We've been looking at other languages as well, like Rust and Haskell, for changing the way we do our programming. I have some colleagues who use Julia all the time for their ML work. But we do avoid classical languages. In fact, last year was the first time in a while I actually ran GCC, first time in maybe like 5 years. And it was kind of fun to rerun a compiler. But you don't really need to do that anymore if you don't want to, write in those languages. Yep.
Well, we are out of time, but again, Jason, thank you very much for this very informative talk. It's greatly appreciated. And for everyone who attended today, on behalf of Stevens Institute of Technology and the Schaefer School of Engineering and Science, thank you all for attending today, and I hope you all have a wonderful weekend. Thank you very much.